So we're talking about radioactivity, and radioactivity is a natural component of our environment. This is not something that man has created to, mess things up. It's very natural. All elements that have more than 83 protons are unstable and thus radioactive, and there are some that have less that are also unstable. The reason that we still have radioactive nuclides present, even though the Earth is very old, is because new ones are constantly being formed, and many of the existing ones decay very slowly. And by very slowly, I mean extremely slowly. So all radioactive nuclei decay via first-order kinetics. Now hopefully that doesn't give you, PTSD or something, but sounds kind of familiar, first-order kinetics. So first-order kinetics is where the rate is dependent on some constant, but it's proportional to essentially the concentration of the substance. So the more substance there is, the faster the rate. Here, instead of a concentration, we're going to use n, the number of nuclei. So the rate constant is going to determine whether this decays quickly or slowly. And half-life, we talked about half-life when we talked about chemical kinetics, but it is very, very useful in talking about radioactivity. Half-life is the time for 1/2 of the parent nuclides to decay to the daughter nuclides. So essentially for 1/2 of the original nuclei to decay. And so for first order kinetics, T1/2 is 0.693 over the rate constant. So nuclides that decay very quickly have short half-lives and large rate constants. They're considered very active, and they'll have many decay events per unit of time. If you have a long half-life, those are considered less active, and those are going to have, they could go hours or even decades between decay events. Very, very slow. So if we look at thorium-232, has a half-life of 14 billion years. So if you started with 1 million thorium-232 atoms, after 14 billion years, you'd have 500,000 left. Right? So 500,000 decayed in 14 billion years. That's not even one every billion years, right? But then going from 500,000 to 250,000, that's also going to take 14 billion years. So one half-life, you divide the amount in half. We should recognize it, but I'm going to point this out anyway. A radioactive sample does not decay to 0 atoms in 2 half-lives because it just gets cut in half every time. Something with a shorter half-life, radon-220, has a half-life of 1 minute. So 1 million radon-220 atoms after 1 minute would be 500,000, and after a second minute would be 250,000. In 10 minutes, it gets down to 1,000 atoms. And so that's decaying much more quickly. So we can look at the kinetics of radioactive decay. Here we've got the number of atoms of radon-220 versus time, and we see this curve, which is characteristic of first order kinetics. And we can look at the half-life on here. Here's 1 million, and going to 500,000 in 1 minute, and then from 500,000 to 250,000 in a second minute, and every minute it decays is cut in half. Now, radioactive nuclides and their half-lives are not something that you sit around and memorize. You just look them up when you need them. So here are some nuclides that we might run into and their half-lives. And we see the half-life varies a lot. Thorium-219 is 1 microsecond, so extremely short. And then up here we have 14 billion years. So a little bit of difference there.
What's the difference in the alpha and the beta?
It's the type of decay. So alpha decay is when the nucleus emits an alpha particle, which is the equivalent of a helium nucleus, 2 protons and 2 neutrons. Beta emission or beta decay is when an electron is emitted. And that happens by, I always get those mixed up. A proton, I get them mixed up. I can't remember. It's either a neutron going to a proton and an electron, or a proton going to a neutron and an electron. I always mix them up.
For beta decay, I have in my notes a neutron going to a proton and electron.
Thank you. So it's a neutron decaying or changing into a proton and an electron, and the electron gets spit out of the nucleus because electrons do not belong in the nucleus. So we can look at the integrated rate law, and this is the same as we did for chemical kinetics. The natural log of A at time t over A at time 0 equals negative kt. For radioactive decay, instead of looking at a molarity, we're going to look at number of nuclei, and that could be measured in moles. So the natural log of the nuclei now divided by the nuclei initially is equal to negative kt. So we can do lots of different calculations using this. So here's an example. Plutonium-236 is an alpha emitter with a half-life of 2.86 years. How long will it take for a 1.35 milligram sample of plutonium-236 to decay 2.1 milligrams? So we're given the half-life there, so let's write that down. Can you hear that kitten? Yes.
Yeah, are those yours?
I don't know what it's yelling about.
That's loud.
It is, and it's not even in the room. Hang on just a minute. Okay, so our half-life is 2.86 years. And then we've got these other numbers here. We've got 1.35 milligrams, and we have 0.100 milligrams. And the equation is the natural log of n at time t divided by n at time 0 is equal to negative kt. Oops. So we're going to need to know what the rate constant is, right? So since this is first order kinetics, we can calculate that. I believe this was an equation we looked at earlier. T1 half is 0.693 over K. So what we're trying to find here is K instead of T1 half. So I can just switch those through the magic of algebra. And we can calculate the rate constant. It's important to keep track of what unit you're using, because you can use different units of time. You just need to remember what you're using. So 0.693 divided by 2.86 years gives me a rate constant of, I should probably keep at least 3 sig figs, 0.242, 3, and the unit there is per year. It's not a very good. So that's the rate constant. What are these amounts? Well, they're masses, right? And in this equation, we're talking about number of nuclides at different times. Well, it's a ratio of this one to that one, and it's the same substance, it's the same element. So we can use the masses, because to convert mass to number of atoms, we would need to use Avogadro's number and the molar mass. And we would do that to both of these, and then when we took the ratio, they would cancel out. So if you want to convert them to numbers of atoms, you can go ahead and do that, but we can save ourselves some time by just using the masses. So it says we're starting with a 1.35 milligram sample. So this is N0, and we want to know how long it's going to take to get to 0.1. So I'm trying to find T here. So T is going to equal the natural log of 0.1 milligrams over 1.35 milligrams divided by the, and there's a negative in there, divided by the rate constant, 0.2423 years per year. And I'm coming up with 10.7 years. Any questions about that one?
Mrs. K?
Yes.
Does it matter the masses if it's in milligrams or grams?
No,
or
it doesn't.
We have to convert to milligrams?
It doesn't matter because the units cancel out. So here in this term, we need to use the same mass unit for both, but the milligrams are going to cancel out. We could use pounds or tons or whatever. It just needs to be the same.
Okay, thank you.
Anybody else? And these are my old slides, so there's no answers given here, so we'll just have to hope that I got it right. Make sure I didn't skip something. There we go. So I kind of cheated and already did this, but mass is directly proportional to the number of nuclei, and there's a ratio in that rate law, and so the initial and final masses can be used instead of initial and final numbers of nuclei. So the rate of decay is directly proportional to the number of nuclei and can be used in the integrated rate law. So we can look at the rate of decay or the mass at time t and mass at time 0. The rate is proportional to the mass. So radiometric dating is using the predictable decay of radioactive isotopes to estimate the age of things. We can do this for rocks or any artifact that contains the radioactive isotopes. Probably the most well-known is radiocarbon dating, and this was devised in 1949. It makes use of a radioactive signature that results from the presence of carbon-14 in the environment. And William Libby won the Nobel Prize in 1960 for this work. It's used by archaeologists, geologists, anthropologists, and other scientists to date the age of a specimen. So this was used on the Dead Sea Scrolls, which were found in 1947, right before Libby came up with this method. Some shepherds were looking for a lost goat and went into a cave near the Dead Sea and found some jars stuffed with ancient scrolls. And so then, what are these? How old are they, right? And so the age of the scrolls was determined using radiocarbon dating. And they were found to be 2,000 years old. And that was like 1,000 years older than anything else that had been found. So that was pretty significant. So how does this work? Well, carbon-14 is the radioactive isotope of carbon, and it is constantly formed in the upper atmosphere when neutrons bombard nitrogen. So the reaction looks like this. Nitrogen-14, which is just regular old nitrogen. There's lots of nitrogen in the air. It's the most common substance in the air. Gets hit with a neutron, and these are going to come from the sun. And it'll turn into carbon-14 and hydrogen. So carbon-14 is radioactive, and it decays back to nitrogen. Here's its equation, by beta emission, and the half-life is 5,730 years. And so this long half-life makes it useful. So because of the continuous formation and decay of carbon-14 in the atmosphere, the concentration of carbon-14 in the atmosphere is nearly constant. So the atmospheric carbon-14 gets oxidized to carbon dioxide, gets incorporated into plants through photosynthesis, and makes its way up the food chain, decaying as it goes, but very slowly. So all living organisms are going to have the same ratio of carbon-14 to carbon-12 as that found in the atmosphere. Because if something is alive, it is continually ingesting carbon, and that carbon from the atmosphere is going to have the same ratio. When an organism dies, it stops incorporating new carbon-14. And so all of the carbon-14 present when the organism dies is all there is. There's no more being added. And so we can look at the decay or the ratio of carbon-14 to carbon-12, and we see that this ratio decreases with a half-life of 5,715 years. Now you might notice there's a difference here. This was 15, the one on the previous slide was 30. They changed it on me, and I missed it in a couple of slides, I think. They updated it. They didn't change it. They updated it. So, does anybody have any questions about the big idea of radiocarbon dating?
No, but what you're saying is now 30, it's now 15.
Can you say that again?
It's 5,730, right? Not 5,715.
I think the 15 is right. I'm just going to look it up because that's important. Not super important, but it's kind of important. Yeah, it's 15. 5,715. That's what's in the newest edition as well. So every living thing has carbon-14 in it, which is radioactive. When you die, you don't get any more carbon-14 coming into your body, and what's there is going to decay. And so we can measure how long something has been dead. The maximum age that can be estimated is about 50,000 years, because at that point the amount of carbon-14 left in the organism becomes too low to measure accurately, because the initial amount of carbon-14 is not very high to start with. We can check the accuracy of this method against objects whose ages are known from historical sources. There have been deviations of up to 5% observed in the atmospheric carbon-14 levels over time, and corrections to that concentration can be made using data from western bristlecone pine trees. They can look at the thickness of the layers and other information about the growth rings in those trees, and they can get information about the carbon-14 levels. So we could look at a problem like this. A researcher claims that an ancient scroll originated from Greek scholars in about 500 BC. A measure of its carbon-14 decay gives a value that is 89% of that found in living organisms. How old is the scroll, and could it be authentic? So, first order kinetics, we've got the natural log of the number of nuclides at time t divided by the number of nuclides at time 0, and that's equal to negative kt. So this 89% corresponds to 89 out of 100, right? So 89 out of 100, we can interpret this as 89 nuclides left out of 100 originally present. So we can take that percentage and use it as the ratio, right? So that's going to be 0.89. It's going to equal what we've got now over what we started out with. If it was 100%, then this would be 1, and NT would equal N0. So that's what this ratio is here. Again, we need the rate constant, and we can calculate that from T1/2. So the rate constant is 0.693 divided by T1/2. And so that's 5,715 years. So that's 1.213 times 10 to the minus 4. Year to the minus 1. So if we solve for t is the time at which this ratio is 0.89. So t is equal to the natural log of 0.89, and put the negative sign in there somewhere, divided by negative 1.213 times 10 to the minus 4.
Wait, sorry, where did the 5,715 come from?
That is the half-life of carbon-14.
Okay, got it.
Good question. So I'm coming up with 961 years. Go ahead and
This
check.
is Kay.
Yes.
So the 0.89 is at the time, and then are we assuming that the 100 is the one at the initial? Are we assuming that like at the initial, like at the? I'm not quite sure why we
So-
just used the.
So
analog.
if we started with 100,
Uh-huh.
at this point we have 89. Because
At like time now.
time now, 89% of that found in living organisms. So when it started, it was 100%. Now it's 89%.
Okay.
Yeah. And that's taking that percent and translating it into this ratio is not a hard thing, but it's easy to forget that you can do that. And so then you can end up on an exam looking at this thing and going, wait, what? What do I do with this percent?
Okay, so the 0.89 equals that entire ratio of
Mhm.
time now and time initial. Okay.
Yep.
Thank you.
Yep. So, 961 years old. Could it be authentic? Could it have been written on in 500 BC? What year is it? 2020? So that would be 2,500 years old, not 961. So, not authentic. Any questions? So radiocarbon dating is limited to things that were once alive. So if you have a rock or a statue made out of clay or something that was never alive, and so you can't use radiocarbon dating. It's also limited to things that are less than 50,000 years old. There are other methods of using radioactivity to date things, and one of them is using uranium. Uranium-238 decays to lead-206, and the presence of the radium-238 within igneous rocks is a reliable measure of the time since the rock formed, since it solidified. So the uranium-238 decays to lead-206. The half-life here is 4.5 times 10 to the 9th years. So we can look at the relative amounts of uranium and lead and figure out how long ago that rock formed.